Hello, everybody, and welcome. This is Professor Thayer with you here today to continue our discussion of the classical wave equation. So the last time we looked at solving the classical wave equation, and we saw when we separated the variables out, that we created a separation variable, which was k equals, well, we didn't know what the value of k was, but the k could be 0, less than 0, or it could be greater than 0, positive, negative, or 0, in other words. And we took a look at the solutions when k equals 0, and we discovered that there were no useful solutions coming out. But we have not yet taken a look at the situation when k is less than 0 or k is greater than 0. So what we're going to do today is we're going to take a look at the solutions when k takes on those other variables. So let's go ahead and get started. I'm gonna share my screen and continue on with our note taking as usual. So let me turn off the camera, turn on the share. Oops, no, wrong thing. This one, share. Share my entire screen, and let's make this full screen. There we go. All right. All right, so the next thing we're going to do is we're going to consider k. This is a classical wave equation. Let's consider k is less than 0. Is less than 0. All right, so let's take a look at our equations we have. We have our partial derivative d squared x of x over dx squared minus k x of x equals 0. And we have d squared t of t over dt squared minus kv squared t equals 0. All right, these are our situations. So now consider k is less than 1. K is less than 0. In other words, let k equal -1. Why not? So now we could also let x of x equals y. Just for simplicity. This is the y function. Okay. So now what we're going to do is sub in k equals -1. D squared x of x over dx squared minus what? K is -1, so we substitute that in. X of x equals 0. So sub in y of x, sub in k equals -1. This is k is less than 0. Okay, next what we're going to do is let's just put in y. So d squared x of x over dx squared. So minus negative is going to be plus, and let's let x of x be y equals 0. So this is sub in y of x. Y of x. This will just match some more standard notations. And now we're going to note, just like we usually do, this is y double prime plus 0y prime plus 1y equals 0. So we see we have second order linear homogeneous differential equation. Right, second linear homogeneous if Q. And now we can deduce our P and Q by inspection. So P equals 0 and Q equals 1 by inspection. In Q. So this is our usual procedure for solving second order linear homogeneous differential equations. So now we have m squared plus pm plus q equals 0, which is our auxiliary equation given. And then we can substitute in the p and q. So we do m squared plus 0m plus 1 equals 0, sub p and q. And now basically this is going to be solved by using the quadratic equation. Negative what's so ax squared plus bx plus c equals 0. Negative b plus or minus root b squared minus 4ac all over 2a. So this is our quadratic equation. This is the general, and this is our quadratic equation. And now we can substitute in. So let's see, negative 0 plus or minus root, what's b squared? 0 squared minus 4 times a is 1 by definition because we made it that way. And c is also going to be 1 all over 2 times a. So a is 1. So now we're going to simplify this. This is sub in into equation. And now we have plus or minus root negative 4 over 2, which gives us plus or minus 2i over 2, which gives us plus or minus I. This is just simplifying the algebra. Okay. So now what we're going to do is we're going to need to deduce the a and b. So m equals a plus or minus bi. This is the general complex form. And the next thing we're going to do is we're going to fill it in. So m equals what's a is 0 plus or minus 1i. This is our solution from up here. Oh, it doesn't look very clear. Let's just write this more clear. Plus or minus I, that's much better. Okay. So now we can get out the information that a equals 0 and b equals 1. Inspection. All right, good. Now we're on to step 3, which is sub into the correct case. Form equation. So this is case 3. Complex roots. So the solution is going to be this generalized form, y to the x, y of x equals e to the ax c1 cosine bx. plus C2 sine bx. Is the general form or the complex roots. All right, next what we're gonna do is we're gonna sub in our A and B value. So A equals 0 and B equals 1. So y of x equals e to the A, what's x, let's see. Oh, sorry, we need to sub in A. A is 0 x times C1 cosine. We know what B is, 1x plus C2 sine. What's B? It's 1x. Yeah, okay. Now anything to the 0 power is 1, so this is gonna go away. And cosine cosine of 1, and so these are gonna carry along. So let's just simplify. So y of x equals C1 cosine of x plus C2 sine of x. So this equation has two forms which can be interchanged by Euler's formula. So it could either be in the trigonometric form or it could be in the exponential forms. Okay, so Euler's formula goes like this. E to the plus or minus IO is equal to cosine theta plus or minus sine I sine theta. Euler's formula. So let's demonstrate the interchange. So the issue is that we want to go in a certain direction, but we actually need some information to do that that is not going to be totally obvious. So what we might do is go ahead and solve this in one direction and then demonstrate we could have done it the other way. So we're going to demonstrate the interchange because we're going to need to have it in the other form for a reason that hopefully will become obvious as we move on. So let us, that doesn't look like an L. Oops, let us demonstrate the interchange. C1 e to the ix. This is the thing we want to change, to interchange. All right, so C1 e to the ix is equal to C1, constant stays the same. So e to the ix, we just take a look here. All right, this is a theta, not a 0. C1 e to the ix is going to be C1 times the cosine theta plus, so since we have a positive sign, we take the plus root plus I sine theta. Substitute the positive root, or it's actually shouldn't be root like that. It should be root like this. So what I mean by that is in the original formula, the plus is on the top and this plus is on the top here. So that means if you have a plus sign like we do here, that you would go with the positive root, R-O-U-T-E. And if you have the minus sign up here, you go with the minus sign down here. So we sub the positive root in. So next what happens is we also need to do the same thing for the C2 term. C2 e to the negative ix. So here's our negative root. This is another thing we want to interchange. So what happens when you have that equals C2 times cosine theta minus I sine theta. So this is sub the minus root because we had the minus sign. All right, so now now that we have a sense of how we could actually use Euler's rule, we could do something a little bit more complicated. This is the one we actually want to do, y of x equals C1e to the ix plus C2 e to the negative ix. A more complicated thing to interchange. Equals, but notice that we've already solved these because we just substituted in, well, we just basically did this by part. So y of x is equal to C1 cosine x plus I sine x plus C2 cosine x minus I sine x. The solutions are above, we just sub in. So now what we're going to do is we're going to do a distribution. So we're going to have equals C1 cosine x plus C1 I sine x plus C2 cosine x minus C2 I sine x. This is just, yeah, that looks messy. Let's distribute. And the next thing we do is we're going to rearrange the terms. So let's just take a little bit of a note here and we're going to do a little color coding. Actually, I think I'll use the highlighter for this. All right, so what we want to do is we want to group together the things that are the cosine terms. So here's a cosine term here, and here's a cosine term here. And now let's change the color of the highlighter and let's do a pink one. And this is the sine terms. So what we want to do is we want to group them together according to the colors. So we could do C1 cosine x plus C1 I sine x. So we have the next we want to put the C2 plus C2 cosine x, right? Because you want the cosine x's together, plus C1 I sine x minus C2 I sine x. So this is just rearrange. All right, now since we have the cosines all together and the sines all together, we can factor out. So what we're going to do is we're going to say C1 plus C2 cosine X plus, now we're going to do some factoring here, I C1 minus I C2 sine X. It's factored out. All right, so we basically rearranged this equation in just using some algebra in order to group these terms differently, because we started by multiplying out and now we rearranged and then we regrouped them. And just to make the point clear, this might help. So here is the sine X stuff, and here is the cosine stuff to help make that more apparent. They've been grouped together. Okay, so now that we have them like so, well, we have some complicated constants. Now we're going to play the same game that we've done before, and that is that you have some constants and you add them together, why keep them all separate? I mean, the constant's a constant. So what you could do is you could define a new constant that's defined as some combination of the old ones. So C1 plus C2 could be C3, and C4 could be defined. So triple equal sign means defined to be. So IC1 minus IC2. That's a 4, and that's a subscript in case that's not obvious. So with these new constants being defined, that simplifies things considerably. So C1 plus C2 is just C3. And anytime we want to go back to the originals, all we got to do is just go back and look over here to what they were equal to. C4 sine X. Great. So now we've factored out two constants. We just rename them, and that's what happened here. So now we have y of x, let's just write the whole thing, equals C3 cosine x plus C4 sine x. So this is demonstrated going from the exponential to the trig form, but we could do the interchange in the other direction. We could go from trig to exponential, and let's demonstrate that. Right, so this one, so the interchange we just did was exponential to trig. Next, we're going to do to demonstrate the interchange in the other direction. So this may all feel like some exercises in tedium, but there is a point to this. Now, so we're going to go trig to exponential. So y of x equals C3 cosine x plus C4 sine x. This was given. What to interchange? C3 was defined to be C1 plus C2, and C4 was defined to be IC1 minus IC2. So you see that we would not have necessarily known to do this before. Let us break out constants. For each of these. Now what we're gonna do is we're gonna sub them in. So y of x equals c1 plus c2 times cosine x plus I c1 minus I c2 sine of x. This is sub in the constant definitions. Now y of x is equal to c1 cosine x plus c2 cos x, I'm just distributing out, plus IC1 sine x minus IC2 sine x. This is distribute. Now we're going to rearrange by putting similar things together. So what we're going to do is we're going to do some grouping. Let us now take a look at the C1s and C2s. So we're going to play the similar game, but in reverse. So let me just pick some different colors we haven't used before. All right, so how about, let's C2 be green. Here's a C2 and C1. Let's let that be purple. I'll use that. This C1 is right here. Okay. So now what we want to do is we want to do this. C1 cos x plus IC1 sine x. So I'm just rearranging C2 cosine x minus I C2 sine x. So notice that what I've done now is I've grouped them back together. So the C1s are now together and the C2s are also together. And so now I'm getting ready to factor out. So this is rearrange. This should be an equal sign. Okay, so next up, C1 can now be factored out. And cosine x plus I sine x plus, now we factor out the C2, and then we do cosine x minus I sine x. Out the constants. All right, so now let's have a look at Euler's formula again. Now we're ready to substitute this back in. So here we can see Euler's formula, cosine theta plus I sine theta. We have cosine theta plus I sine theta. It's just in x's instead of theta. But different variable name does not change the validity of using it. So we are good to go and to apply Euler's again. So y of x equals c1 e to the ix plus c2 e to the negative ix. This is y Euler's formula. So then, the transformation has been done in both directions. And this is relevant because our solution to the wave equation was actually solved in the trig format, but we know that we could also solve it in the exponential format. So now we can select whichever one is more convenient for us. So this is great because now we have the solution in either form. We now have the solution in both trig and exponential. So we could also just be explicit about the constants because our C1 and C2 from our solution are actually C3 and C4 of page 40. So we need to just be very careful about that. So I'm just going to rewrite this. I'm not going to rederive the whole thing, but I'm just going to rewrite this. Okay. For our actual solution. Because there's a bit of confusion on the letter use. 5x equals C1 cosine x plus C2 sine of x. This is a solution from above. And then we have some, so we were going to basically repeat the same steps. It's the same procedure. It's just that the constant names have changed. And I just want this to come out in the exact names of the constants that we're using. So now y of x equals c sub a e to the ix plus c sub b e negative e to the, oh no, that's wrong. E is not up there. E is down here. E to the negative ix. This is y Euler's rule. All right, now k is less than 0 yields some interesting results. The general solution to the wave equation is a superposition of the normal modes. So k is less than 0, which we've already been considering. That case, let k equal negative beta squared. This will be for convenience. In a moment. So you could let your k be whatever variable you want. So why not let it be something squared? We're going to need to be doing some square rooting soon. So now we're going to have d squared x of x over dx squared equals, oh no, plus, sorry, plus negative k x of x equals 0. And we have d squared x of x over dx squared plus, now we're just going to sub this in, beta squared x of x equals 0. 7 our beta definition that we made above. Then we apply the procedure for solving second order linear homogeneous differential equations. So what's step 1? Okay, you write out the equation d squared x of x over dx squared plus beta squared x of x equals 0. Now we're going to line this up, y double prime plus 0y prime plus beta squared y equals 0, p equals 0, and q equals negative beta squared. Sorry, positive beta squared. All right, next, we write the auxiliary equation. M squared plus PM plus Q equals 0. That's the auxiliary equation. This is by inspection. Here's our auxiliary equation. Next, we're going to sub in. So M squared plus 0 M plus beta squared Q. Beta squared is sub in equals 0. This is just sub in P and Q into the equation. And now we're going to solve for M using the quadratic equals negative 0 plus or minus root 0 squared minus 4 times 4 times 1 times beta squared 4AC all over 2A, which is 2 times 1. This is just quadratic equation. Which I've just filled out. And equals plus or minus. Now we're going to need to solve this thing. Okay, so negative 4 beta squared over 2 equals plus or minus 2 beta I 2. So you see that having the beta squared as our constant was useful because now that allows us to just cancel that out. So, and here we're going to cancel the 2's. Equals plus or minus I. This is solved. And simplifying the equation. Great. So now the next thing we need to do is we need to deduce the values of A and B. So M equals A plus or minus BI. This is the general complex form. M equals 0 plus or minus beta I. This is just substituting in our actual values. So A equals 0 and B equals beta Reduce A and B by inspection. Oops, sorry. This one. All right. Next, we have y of x e to the ax times c1 cosine bx plus c2 sine bx. Let's say okay, sub in e to the 0 x times c1 cosine beta x plus c2 sine beta x. Okay, anything to 0 power is 1. Oh, we got equal sign. There we go. Anything to 0 is 1. So that goes to 1 equals c1 cosine beta x plus c2 sine beta x. X of x equals y of x equals a cosine beta x plus b sine b beta x. A is defined to be C1 and B is defined to be C2, just to be consistent with more canonical notations. So at this point, this has been pretty much a repeat of what we've been solving before. So now what we need to do is we need to apply the boundary conditions. So x of 0 equals 0. And x of L equals 0. So again, these mean that the ends are bound. X of x, so we're going to take our solution from above, a cosine notice this have both beta and b in it, so this is the solution from above. And we're going to substitute in the condition, so x of 0 equals a cosine beta of 0 plus b sine beta times 0 equals 0. Recall that the sign of 0 is 0, so this term goes to 0. This is just sub in x of 0 equals 0 bound. And then we can just simplify this. This is equal to a cosine 0 equals 0 and a1 equals 0. What is cosine of 0? Cosine of 0 is 1. So a times 1 equals 0. In other words, A equals 0. All right, that's our first solution. And here we simplify again. Next, we solve the second boundary. So x of x equals a cosine beta x plus b sine beta x. This is the solution above. I just copy that down. Now we're going to sub in. So x of L equals a cosine beta of L plus b sine, wrong one. B sine b beta L equals 0. This is subbing that x of L equals 0 from bound. Next, we recall that a equals 0. So if a is 0, this means we have 0 cosine b of L plus b sine beta of L. But multiplying anything by 0 makes that term be 0. So that's gone. So the next thing we do is we simplify this. So that means that x of L equals, oh no, I got that wrong. This one is B. Notice there's B and beta here. B, this one is B, sine beta L equals 0. Let's simplify. Either B equals 0, which is trivial, and therefore not interesting, or sine beta L equals 0. Finally, we have an interesting answer. We call sine theta equals 0 for theta equals 0, pi, 2 pi, 3 pi, and so on. So theta L equals n pi for n equals 1, 2, 3. That is integral numbers of pi. We will omit n equals 0. N equals 0 is a trivial solution. That implies beta equals 0, right? So that's why we're going to omit 0. We start 1. So we'll start with pi. All right. So then, x of L equals beta sine. No, that's going to be more clear. This is B. B sine beta L equals 0. That's from above. I'm going to invoke that again. X of x equals B sine B beta x equals 0. I just want to use x instead of L. I can change my variable name if I feel like it. X of x equals B sine n pi x equals 0. This is sub in. So we've just done the substitution in here. And now x of x equals B sine n pi x over L equals 0 for all n in n. So those are integers to make per unit length. So the reason why we have this divided by L is because we want the answer per unit length. And so we just divide out by the length of the box size. So then to formalize this, x of x equals B sine n pi x L or n in n. This means per length. What that means is the positional equation. Okay. So that was the positional equation only. We also have the temporal equation, which we have not yet solved. All right, so we're gonna follow the very similar derivation of this. So we got d squared t of t minus kv squared t of t equals 0. Oh, d t squared. Now, this is the temporal equation. Okay, dt. Oh, and d squared t of t over dt squared plus beta squared b squared t of t equals 0. This is let k, same trick we played before, equal negative beta squared as just as we did for the positional one. And now we have oops, y double prime plus, I think I'm pressing a button by mistake, plus, oops, no, wrong thing. plus, we have to use this, plus 0y plus beta squared v squared y equals 0. This is right in the Newton's notation. P equals 0 and Q equals beta squared v squared. Deduce P and Q by inspection. Step 2. The auxiliary equation. All right, m squared plus pm plus q equals 0. This is the auxiliary equation. So we have m squared plus 0m plus beta squared v squared equals 0. This is the sub in p and q, and then we can do the quadratic. It's not very neat. Let me try to write neater. Quadratic. So we have m equals -0 plus or minus root 0 squared minus 4 times 1 times beta squared b squared all over 2 times 1. So now we're going to just simplify this. Over 2 equals plus or minus 2IBV over 2, and the 2's go out. 2 is gone. Equals plus or minus IB. This will simplify. M equals A plus or minus B. I, the general form. M equals 0 plus or minus BVI. This is our subbing in. A equals 0. Hey, my pen stopped writing. What's up? A equals 0 and B equals BV. Reduce A and B. Now we move on to step 3. This is a sub-in case and form that are appropriate. So this is a case 3. Complex roots. Y of x equals e to the ax times c1 cosine bx plus c2 sine bx. This is the general form. The complex roots. Now we're going to sub in A and B. So here we have equals e to the 0x times c1 cosine bv times x plus c2 sine bv, oops, times x. This is sub A and B. Next, C1 cosine BV x. Yeah, because we need to note this. Oops, this goes anything to 0 power is 1, so that essentially goes away. Hey, my pen just went away. Not sure how we get that back. All right, well, anyways, let's keep going. Okay, BV of x plus, oh, pen's it back, C2 sine BVX. Okay, and this is just simplify. All right, good. But let's use t since this is the time equation. So I'm just gonna switch my variables up. T of t to use t instead of x. C1 cosine BVT instead of x plus C2 sine BV beta VT. All right, that's just changing it. And now we have multiple constants, so let's combine. Combine them. So we're gonna make some substitutions. So omega n is defined to be B and n pi. Oh, that's not clear at all. Sorry. N pi v over L. To give t then is equal to d. So we're just playing the same trick we were doing before. Cosine omega sub n t plus some new constant e sine omega sub n t. We would now normally apply the boundary conditions, but we don't actually have any boundary conditions available for time. Note, time boundary conditions are not available. So that means we're ready to write the equation. U of x and t for both the position and temporal halves. So u of x and t equals x of x, t of t equals b sine n pi x over L times b cosine omega sub n t plus e sine omega sub n t. Oops. All right, so remember that we started off with the separation. We started off by having the positional information. All right, this is the position. And we also had the time side. And so we had solved these two now independently and separately because we, well, that's what we just spent our time doing. And we have recently just finished the time side, which gives us our final solution. All right, this writing could use some improvement here. Let me just improve this. It's omega sub n of t, omega sub n t, and this is a closed parenthesis. It should be similar size to the other one. Okay, that looks much better. So here is our position solution, and here is our time solution, which are multiplied together because we had assumed the separability. So we have now completed that. With this in mind, we can distribute the constants and combine these up. So we have the constants b and d and also e, but who wants to have too many constants? So this is equal to sine n pi x over L b dot b cosine omega t plus b times e sine omega sub n t. This is distribute. I just distributed b. Next, what I'm going to do is I'm going to play the constant collapse thing again. So we're going to do sine n pi x over L times f cosine. Right, so we now have two of these together again. We're going to collapse those. Cosine omega sub n t. This should also be sub n, omega sub n t. Plus, and now these two I'm also going to combine. G sine omega sub n t. This is for n equals 1, 2, 3. It's actually always been like that, where f is defined to be BD and G is defined to be BE. So we've collapsed them. So now we have U of x and t equals sine n pi x over L times f cosine omega sub n t plus g sine omega sub n t, again for n equals 1, 1, 2, 3, dot, dot, dot. Whoa, oops. That's not motion I anticipated. All right. Not totally sure what just happened there. All right. Now this is a solution to the differential equation, but since each u sub n of x and t is a solution, their sum is also a solution. So we can also write, okay. This is the solution to the diffie q. Their sum is also a solution. So we can write then u of x and t equals n equals 1 to infinity f cosine omega sub n t plus g sine omega sub n t sine n pi x over L for n equals 1 to blah, blah, blah. Now consider that sine and cosine are actually the same function with an offset. So in fact, sine and cosine could be written in relation to each other, and we would have some kind of translation constant between them. Which we might define. So what we can do is we can now transform this like so. You have x and t equals the sum of n equals 1 to infinity of a sub n cosine omega n t plus p. This is our offset sine n pi x over L, which is equal to n equals 1 to infinity u sub n of x and t. Let's consider the interpretation of the classical wave equation solution. When the string is plucked, its shape is gonna get, or the displacement, when we say the shape of the string, the displacement will evolve according to u of x and t in the displacement equation. Each u of x, u sub n of x and t is gonna be a normal mode, and the time dependence of each normal mode then is gonna represent a harmonic of motion. So let's just summarize these things. When the string is plucked, its shape will evolve according to u of x and t, the displacement equation. Each u sub n of x and t is called a normal mode. The time dependence of each normal mode represents a harmonic motion of frequency. A harmonic motion of frequency. This is mu equals omega sub n over 2 pi equals v sub n over 2L. This is the velocity. Omega sub n equals v equals n pi v over L, or n equals 1, 2, 3, blah, blah, blah. The quantized numbers are going to actually give rise to the different waves, so it's going to look like this. To the different waves. I'm going to draw a couple of waves here. All right. This. All right. And this is for my benefit, the thing here. We also have those. This should be divided into thirds. Oh, good. I kind of have. Hey, what just happened there? Sometimes I think I press the buttons here and they do things that I do not expect on the pen. All right. Exit. What the heck? Why is that deleting? No, that should be deleted. No, it's not even. Let me delete this. Should be thirds. 1, 2. All right, that's close enough. Dude, what is going on here? Not touching any buttons. 1, 2, 3. All right. I do not understand why I cannot draw this and keep it here. All right, last attempt. 1, 2, 3. It's thirds, roughly. Just pretend. I don't dare to write on this again. All right, n equals 1. This is number of nodes is 0. N equals 2. Number of nodes equals 1. So the nodes are these dots that are in the middle. N equals 3. Number of nodes equals 2. All right, so standing waves result from binding the ends of the string. All right, so then let's take a look. We have now completed solving our wave equation. We today have worked on solving this for the situation of k is less than 0. So, and the k is the separation constant. When we use k is less than 0, we needed to solve the classical wave equation. So we needed to solve the positional one, which is this first one that we solved. And then we also needed to, we wanted to also demonstrate the interchange from the exponential to the trig, because sometimes we want to use the other solution. And then we had this, okay, so we had the general solution from above, and now we wanted to make use of that trig, so we did so. And here we're applying the procedure for solving the second order linear homogeneous differential equation, which is what we did here. And then we needed to apply, okay, so then we got this answer, and then we needed to apply the boundary conditions, which we're doing down here. So we started off with x of 0 equals 0. And first of all, we got a equals 0. And then we used the other boundary condition, and also knowing that a equals 0, which simplified our situation pretty much a lot. So we either had another trivial solution, b equals 0 for one of the constants, or we had the solution that the sign of BL equals 0. Finally, something interesting right here. And notice that this will happen. So how do you get the sign of something to be 0? So that means that you have to have something that's an integral number of the pi's, and this is where the n, the quantization got introduced. So then we could go through and we could take a look at look when we have x of L, right? We did, and then we switch that to x, and we can then solve this, and this was our formalized position equation right here. But then we needed to also solve the temporal one. So here we went back to the beginning, and we started with the temporal equation, and we solved this in the usual way using the second order linear homogeneous differential equations. And then we so again, we had complex roots, so we came through and solved all of that. And after we solved this, well, normally we'd put in the boundary conditions, except that there aren't any. So next we came down here, and we were now able to combine both of these sides, right? So we solved for the temporal and the position, and we were able to join those back together. So here's what we're doing that right here, position and time being combined together. But we wanted to just play some tricks with this to simplify this, because we have a bunch of constants in there, and we could really get rid of those constants and just join them together, which we did. And we also wanted to keep in mind that we got a solution for the equations, but also multiples of that equation would also be, the sum of them would also be a solution. So what we did is we took the sum of these things. And also we considered that sine and cosine are really actually the same function, just with an offset phi. So we then rewrote, and we were able to just keep track of this offset phi and put it all in terms of the cosine, which gave us our very final form of the equation, which we have ta-da right here. So we could go ahead and star this one. This was our final equation that we got. And then we took a look at what the interpretation of this is. So more or less what this means is that it means that we have the quantized numbers, which came from the sign going to 0, which happens at integral values of pi, which gave us our n. We had the quantization giving rise to these standing waves. And the standing waves then happen when n equals 1, 2, and 3, and so on, right? So of course there are many more of these pictures. But we see that we have n equals 1 has one wave, right? That's bound on the end, so there are no nodes. When you have n equals 2, you have a node in the middle. That is, it goes through 0, right? 0 displacement. And you have 2 lobes of displacement on either side. And then we have n equals 3, which gave me a lot of trouble drawing because it kept deleting for some reason with the pen. But anyways, you get the idea that this now has 3, and then you could continue on 4, 5, and so on, which give you the harmonics in the higher order. So if you play a musical instrument, this is exactly how you get the overtones on the strings of the instrument. And you probably know that changing the length of the string by, for example, using a fretboard like on a violin or a guitar, viola, cello, and so on, is what is going to change the sound of the instrument. And the wave then has a standing wave, and these alternative solutions, right? Standing waves with nodes and so on are exactly what give the instrument its sound. And so when these occur, you get the overall movement of the string to, in fact, actually be the superposition of all of these normal modes. So we have now solved the classical wave equation. Congratulations. Alrighty, well, thank you so much for joining us today for solving the classical wave equation. I hope you've enjoyed learning about this, and this is going to have many things that are going to carry over for our solution in the quantum mechanics. So I hope you found this helpful and instructive. Next time, we will move on to solving particle in a box and all of the things that go along with that. So thank you so much, and we'll see you next time. Bye-bye.